Okay, let's dive right into this. Welcome to today's explainer. We're going to tackle a massive, absolute foundational pillar of modern computer science, database systems. We're going to take all those abstract, kind of invisible gears of data management and break them down so you can actually see how the digital world organizes its most valuable resource.
Here's our roadmap for today. We'll start with data versus information, move into the database advantage, look at levels of data abstraction, peek inside DBMS architecture, and wrap up with the database administrator.
All right, kicking things off with Section 1, Data versus Information. So in computer science, when we say data, we're really talking about raw, isolated, completely unstructured facts. Think of a random number, a date, maybe just a name. On their own, they literally mean nothing. They completely lack context. But information, that is what happens when we process, organize, and structure that raw data into something you can actually use. It's kind of like the difference between having a giant, messy list of random atmospheric metrics and having a clear weather forecast that tells you, hey, you should probably grab an umbrella today.
Moving right along to Section 2, the database advantage. To truly appreciate modern systems, we kind of have to look back at how things used to be. Think of a traditional file system like a chaotic, overflowing physical filing cabinet. Every department has its own cabinet, files get duplicated all over the place. Someone takes a folder out, loses it, and trying to find one specific cross-reference piece of paper, yeah, that takes hours. It is wildly inefficient. But a modern database system, it totally centralizes that chaos. It creates this single, beautifully organized repository where information is logically linked and literally instantly searchable. It's a monumental leap from physical chaos straight to digital harmony.
Now, this advantage really boils down to 4 crucial fundamentals. First up, data integrity. This ensures our info is strictly accurate, no conflicting records floating around. Second is security, meaning we apply strict access controls to really lock down that sensitive data. Third, we have scalability. This is a game changer. It allows the system to grow seamlessly, from handling hundreds of records to billions without just crashing. And finally, efficiency, which just means you can retrieve incredibly complex data in literal milliseconds.
Which brings us to Section 3, levels of data abstraction.
To manage all this information efficiently, databases use a highly structured, layered approach to abstraction. Step 1 is the physical level. This is the absolute lowest level. It deals with how the data is actually physically stored on hard drives and servers. Step 2 is the logical level. Here is where we define exactly what data is stored and the complex relationships between that data, but without worrying at all about the physical bytes on a disk. And finally, step 3, the view level. This is the interface the end user actually interacts with, cleanly hiding all that super complex logic operating behind the scenes.
Now, the real magic here is physical data independence. I know it sounds super technical, but think of it like driving a car. You don't need to know exactly how the combustion engine is firing just to turn the steering wheel and drive to the grocery store, right? The engine's mechanics are completely independent of your interface. In databases, this means we can swap out hard drives, upgrade our physical storage, or totally change how data is written to a disk, and it absolutely won't break the logical data organization or crash the applications that rely on it.
Let's look a little deeper with Section 4, Inside DBMS Architecture.
To truly master this subject, it's just not enough to know what a database is. We have to really pop the hood and look closely at its internal structure. We need to apply computer science engineering theory to examine the query processors, the storage managers, the transaction modules. By systematically analyzing how all these internal gears interact, we unlock this deep, incredibly functional understanding of how the entire system actually breathes and operates.
And finally, Section 5, the database administrator.
The ultimate mandate of the database administrator, or DBA, is to literally interpret the process of data management. Look, a database doesn't just run itself. It requires a visionary, someone who completely understands both the raw physical architecture and the high-level business logic that the end users actually need. They are essentially the interpreters, standing right between the machine and the human enterprise. In practice, this means the DBA is the one actively managing that complex, multi-tiered system architecture we explored just a minute ago. They oversee the overall functionality, ensuring that integrity, security, and efficiency never drop. And crucially, they drive the adoption and significance of specific structures, most notably relational databases. Because relational databases, which organize data into these tightly connected tables, they really are the foundational ecosystem for most modern businesses. And the DBA? They're the ultimate guardian of that ecosystem. Which brings us to the end of today's explainer, but I want to leave you with a really critical self-learning question. We've talked extensively about the architecture and the undeniable importance of traditional structured databases, but our digital landscape is vast and it is changing rapidly. Beyond the relational model, what other types of databases actually exist today to handle the massive, unstructured chaos of the modern web? Because as data continues to evolve, so too must the architecture that holds it. Something to chew on. Until next time, keep exploring.